Good evening, everyone. Am I audible?
Yes,
Yes, sir, you are audible.
Yes, sir. Audible, sir.
Yes, sir.
Thank you very much. Welcome to day 3 of 5 days ATAL FDP on quantum computing and artificial intelligence, convergence and applications. Today, we have an industry person as our resource person, Shalini D. She is working as lead quantum AI researcher and educator innovator. She is a bestseller in Udemy. She did her MSc in quantum technologies from Spain. She earlier worked as system engineering and currently working in the area of quantum AI, Fractal, quantum AI lab, heading projects in quantum algorithms developments, focusing on real-world applications in quantum chemistry and quantum machine learning. With this, I welcome Shalini ma'am. Ma'am, are you?
Hello, sir.
Are you
Hello,
able?
sir. Yes, sir.
Ma'am?
Yes, sir. I'm there.
I'm sharing screening with you, ma'am. Please.
Yes, sir. Sure, sir. Sure. Thank you. Hello, I am very happy to be a part of this FDP faculty development program today, and I'll be hosting this session 5, and tomorrow session 7. So I'll be switching off my camera because of some internet issues and bandwidth, since so many people were joining. So I will now start my session on Boolean algorithms, the Boolean functions and classical operations.
Yep,
So, yeah. Thank you. Is my screen visible?
Yes, ma'am.
Okay. Super. Awesome. Thank you so much. So let's start the session. Today, I am Shalini Devendra Babu. Let me give a small introduction. Even GRS Murthy sir has given a beautiful introduction about me. I'll just give some more details about me. So this is me. I'm Shalini Devendra Babu. I'm lead quantum researcher at Fractal Analytics. And I published 3 books on quantum computing till now. And I have 2 courses in Udemy and Coursera. And I'm also a mentor at TopMate. And I've been featured in Times Square, New York, the Billboard twice. So this is my small introduction, and also I do research in the intersection of quantum and AI, and my main area of research is quantum hardware, and I'm more interested in the quantum hardware session. However, my present job requires more on the software side, so I do research in the quantum plus AI domain, where I focus mostly on material science and life sciences application. Also, I'm exploring the domains in quantum finance and quantum error correction. So this is a small introduction about me. You can just find me on LinkedIn and we can get connected there. Thank you. So today's session is about the quantum versions of quantum or classical operations, reversible classical gates, and Boolean function oracles. So before starting any topic, I would like to introduce about the functions and Boolean functions. Why I'm starting with the functions and Boolean functions. So I will mention that very soon in the upcoming slides. So let's start with the function. So what is actually a function? So function is actually a very generic mathematical term that take any real numbers and complex numbers. But a Boolean function only receives the input as zeros and ones, whereas a function actually can take input as real numbers also and complex numbers also. But a Boolean function takes only zeros and ones as the input and give the output as zeros and ones. So we all understand how come this Boolean came from. So it came from the scientist called George Boole. He's a mathematician who invented the Boolean algebra, which is a system of logic using the values true or false. In the numerical term, we call in the numerical term, in terms of functions, we refer the true and false as 1 and 0, 0 bit and 1 bit. Okay, so that's the difference between a function and a Boolean function. So these Boolean functions actually are the base behind the construction of the classical logic gates, such as AND gate, NOR gate, OR gate, and XOR gate. The reason why I started with a function and a Boolean function is for any kind of circuits. For example, you take a circuit, and a circuit is made up of a lot of gates, right? So gates are actually the byproduct. I mean, not the byproduct. The gates are actually the product of a final product. but the math behind is not well studied at present. So the original math behind designing the classical circuit or even a quantum circuit is actually a function. So functions are the math behind designing quantum or a classical circuit. So that's the reason why we need to know the difference between functions and Boolean functions, and we need to understand at least the foundations of the functions of the Boolean functions. So yeah. So you must remember that sometimes we say AND function, NOR function, XOR function instead of AND gate, NOR gate, XOR gate, or OR gate. Because why? Because this is the reason why I introduced with the functions. Because and these kind of gates are actually made. The foundation has been built with the help of functions. So why we call it as a AND function, NOR function, OR function, XOR function. Okay. So the Boolean function can be actually represented as, in a proper mathematical term, we represent the Boolean function as 0 and 1 to the power n. And this is actually the input. 0, 1 is the input, and 0, 1 is the output. Okay, so I've explained what is the meaning of 0, n. This is a function that takes n input bits, and the output is actually usually a single bit. Okay. And the Boolean functions actually are mostly irreversible in nature, which means in classical computation, the bits are actually overwritten. The energy or information loss isn't a problem in the classical computation, but the lost information is dissipated in terms of it. So we will understand the irreversibility of the gates when we discuss more about the types of function types. Okay, so the reason behind another reason behind studying the Boolean function is because the classical gates are actually constructed with the help of the Boolean functions. So the Boolean functions are actually irreversible in nature. So what is the meaning of irreversible? Irreversible means if you do a computation and you get an output, but when you reverse that, you can't reverse the output to get the original input state. So that's what irreversible means. And classical computing follows these Boolean functions, and the Boolean functions are mostly irreversible in nature. So if the Boolean functions are irreversible in nature, then you understand that the classical gates, which are designed with the help of Boolean functions, must also be irreversible in nature. Okay, so what is the issue? So what is the main concern in quantum gates? We will discuss about in the upcoming slides. So this is such an interesting and important topic we need to understand in a very brief and a very storytelling way, so that it is kind of helpful to have a connection between the algorithms and the Boolean functions, because that's a very important connection. Because until and unless you know the Boolean functions, you can't understand what is the meaning of oracle. If you don't understand oracle, you can't understand what is the meaning of quantum algorithms. So I'm building a base of why we need to understand the Boolean functions. Okay, so in quantum computing, we can't just use the Boolean functions. Why? Because classical computing only needs the classical computing doesn't have any problem if the Boolean functions are irreversible. Because if the functions are irreversible in classical computing, the information is lost. If the information is lost in classical computing, that information lost is generally dissipated as heat, and HEAT. Okay, so that doesn't do much with the classical part. But in quantum computing, this is very much serious concern, because the Boolean the functions should be reversible in nature. Only when the functions are unitary, reversible means unitary. Only when the functions are unitary, the gates can be constructed in reversible in nature. The quantum gates in quantum computing should follow the quantum mechanical laws. The quantum mechanical laws state that the quantum gates must be unitary in nature. So we need to adopt the Boolean function from the classical gate to use it in the quantum domain. So we will see how do we adopt the classical function as a Boolean function used in the classical computing in quantum computing. We will see the upcoming slides. Okay, so I think, yeah, I've explained this slide a bit more in depth, but I will just read out to you. So Boolean functions are adopted into quantum by using an extra bit. Okay, so this is another important point. So how do you adopt a Boolean functions which are irreversible in the classical computing into the quantum domain, where the quantum gates should be constructed in such a way that they should be reversible. So how do we do that? We have to do that by simply putting an extra bit, by adding an extra target bit and using an XOR function. So this actually makes the Boolean function unitary. If the Boolean function is unitary, which means unitary means you're reversible in nature. So that's how we introduce the Boolean functions, which are irreversible in classical computing by nature, into quantum domain, which are reversible in nature. And that's the whole point of Oracle. So this actually gave a good introduction of an oracle. So oracle is nothing but a black box. So what is the meaning of black box? We all know, we have all heard about the meaning of black box in aeroplane and all, right? So we have black box in aeroplane where we where the information is recorded. Every single information happening in the cockpit is recorded in the black box. It's something very, very similar to that. So Oracle is a black box. We don't know what actually is inside the black box. But we know the computation, what's happening inside the black box. Okay, so what actually is Oracle? Oracle is actually made up of the reversible Boolean functions. Means just now we saw in the previous slide that we are adopting the Boolean functions in the classical computing into the quantum version by adding an extra target bit along with the XOR function. So that's what an oracle is made up of. An oracle is made up of a Boolean function, which is in the unitary version of the Boolean function, which can be used in the quantum domain for implementing the quantum algorithm. So this is the importance of understanding the Boolean functions and how we adopt into the quantum form. Okay, so this image u underscore f is nothing but a unitary function, and this is nothing but x and y are the inputs. So this vertical bar and the right side one is right side arrow is nothing but the kit version. Dirac notation. We call it as a Dirac notation. And when the input is actually into the this x comma y is again an output. The y so this y is actually the extra target bit which we are using to adopt the Boolean classical computing, the classical version of the Boolean function to the quantum version. So this y is actually the extra bit we are adding. Okay, and then we are doing the XOR function. So we are representing the theoretical in the mathematical form in this way. So this is actually what an oracle is, and this is something a very simple diagram. So inside this oracle, you have this Boolean function, this reversible form of the Boolean function, and that's what an oracle is made of. Oracle is made up of a unitary version of the Boolean function. Okay, yeah. So input you have x and y. So y is an extra target bit which we are including. Okay, and then x is an input bit, and output is like x comma y XOR f of x. Okay, so in this case, x is preserved. X is preserved means why x is preserved? X is in quantum computing, the input should be preserved. In the classical computing, if the input is not preserved, that's not a problem, because the information is lost, because classical computing is developed in such a way that even if the information is lost, that lost information is dissipated in terms of heat. Okay, so we will see that in the next upcoming slides. So in quantum, if you're adopting a Boolean function into the quantum version, you should preserve the input. So why this x is preserved here and y is modified by f of x using the XOR function. You don't have to worry about this slide. I'm going to share my screen, and I will show how do you actually adopt by solving some examples. I will write and show you. So in the upcoming slides, like in after 10-15 minutes. Now coming to the main point. So how do we actually build an oracle in reality? Again, take a Boolean function. So for example, f of x1 comma x2 and xn. So these are the functions, Boolean function, right? So this if this is a function and this is an input, x1, x2, x till x1 are the input. For example, we can take the AND function and make it reversible. How do you make it reversible? Add an extra bit. So this is the form you can represent, and the inputs are preserved and the output is written into y. Okay. Now coming to the main point, why are we actually using the oracles? many quantum algorithms are actually designed to query a hidden function. Okay, so we'll be understanding with the these are the theoretical parts. Okay, so tomorrow I have a session about the Simon's algorithm. In tomorrow, so I will explain what how to implement and how to solve these kind of queries within Oracle. Okay, so today we can understand how why oracles are used in quantum algorithms and why can't we use it directly. Okay, so to be very precise and to be very short and straightforward, many quantum algorithms are actually designed to query a hidden function. Query means, if you go in the previous slide, input, we are giving input, right? The input, we call it as a query. The technical term is giving a query. So you give a query as an input, and oracle is built upon with the Boolean reversible Boolean function. So if you give a query to the oracle, you get an output. Okay. Because in real life scenarios, because quantum is actually developed to solve some real life issues. In real life issues, we don't know the structure of the problem, whereas we only have the ways to know whether it is correct or not. Okay, so for example, when you search a database, when you search among multiple databases, you don't know where the right item is, but you can test each one. I mean, you can test each one separately, individually. Also in cryptography, you don't know the exact key, because there is some in cryptography you have someone called Alice, Bob, and Eve. Okay, so in cryptography, if you need to have a secure communication, you should not share the key with the other person, right? So you don't know the key, but you can test if a candidate decrypts correctly or not. So again, we don't know the actual structure, so we needed to test and check. We have to keep doing the trial and error method to understand the solution, to understand the best possible solution. So why oracles are actually used to get the best possible solution with the help of superposition and interference. I mean, those two are the important points. With the help of superposition and interference, you can actually get the most possible solution. So you can consider oracle as a tool for experimenting and not as a proper solution. That's the reason why we use oracles in quantum, because if you want to search something in a millions among a million, for example, you have a single 1 rupee coin, and you're putting that 1 rupee coin among all the 2 rupee coins, so you have multiple millions of 2 rupee coins. Okay, so in order to search that, it takes a lot of time, right? So the quantum actually helps in finding the best possible way to find that 1 rupee coin which is among the 2 rupee coins. That's the importance of building an oracle. Okay, yeah, so instead of being told the function experimentally, you are only given an oracle access. The quantum computer then actually query this oracle in superposition. So the input is actually is in the Hadamard one. I mean, using the Hadamard gate, you keep the input state in the superposition one. Okay, by using Hadamard gate. Hadamard gate is actually a quantum gate, purely quantum gate. With the help of Hadamard gate, you can make input state into a superposition state, and then you can give that query into the oracle, and then oracle will find the best possible solution and it will give an output. And that's the whole brief idea about the oracle is, and that's the whole brief idea of how quantum algorithms work. So every quantum algorithm has an oracle. So in Simon's algorithm, we'll be seeing oracle tomorrow. We have an oracle. I will explain that. Actually, when I explain Simon's, when I'll be explaining Simon's algorithm tomorrow, it will make much sense what I'm saying at present. Okay, so yeah, don't worry about this much amount of mathematics. Like it might look a bit overwhelming, but it's kind of very easy to understand. Okay, so as I mentioned, if you want to give a query, the query is actually an input. So the input is actually made into a superposition state. Okay, so the input is actually made into a superposition state, and then you need to that query is given inside the oracle. So when you give inside the oracle, it finds a best possible way to find the solution for the problem, and that's what we represent in the mathematical terms. Okay. Okay, so why this helps? This is the main question. Why this helps? Once all inputs are entangled with outputs, quantum algorithms use interference to amplify the right answers. That's what I was saying you. So among so many millions of 2 rupee coins, you have dropped 1 rupee coin. Okay, so with the help of interference and superposition, so when you give a query, you make that input into a superposition state by using an Hadamard gate. Okay, so when you give that query into the oracle, it finds the right possible answer. I mean, in a shortest time as possible. Okay, so that's the reason why this oracle helps. For example, in Grover search algorithm, you use this oracle to find which amplifies the marked solution. Okay, Grover search algorithm is nothing but in among millions of database, you search one. For example, same example I can give you. You're putting one rupee coin in among the 2 rupee, and it finds the easiest way to find that 1 rupee coin. So it searches the database more effectively. And Simon's algorithm we are going to see tomorrow, which this extracts the hidden XOR mask. I mean, in Simon's algorithm, we are going to see the hidden string, called S. Okay, in that we use XOR function and all, and that's a separate story. We will see that in tomorrow's session. And Deutsch Josa, you might have already discussed about in the previous session, if I'm not wrong. So now coming to the gates. So till now we understood what is function, what is a Boolean function, and what is an oracle, and why oracle is used, and how oracle is helpful in the quantum algorithms. I hope that is clear. To summarize, I can even summarize again. So the first point is a Boolean function. So function is nothing but it's a mathematical term which uses real numbers and the complex numbers, and Boolean function only uses zeros and ones. Okay, so oracle is nothing but a Boolean function which is converted into the reversible unitary version of the Boolean function to be used in the quantum algorithms part. So that's what an oracle is. Why we are adopting the classical version of Boolean function into the quantum form? The answer is because the classical gates are actually irreversible in nature, but the quantum gate should be designed in such a way that it should be reversible in nature. So the main math behind designing any circuit is functions. So the functions which is used in designing a classical gate is irreversible. So we needed to make the Boolean functions reversible, and how do we make it reversible? By adding an extra bit and an XOR function. So that's how we make a irreversible into a reversible. I hope that is a bit more clear now. Okay, now coming back to the gates. So yes, does anyone have any questions? Okay.
You can unmute and ask the questions.
Okay, fine. I think no one has questions till now. Fine. Let's continue. So actually, gates are, again, coming back to the point. So gates are actually called as functions. We have already discussed this. And because gates are applied to the input values to get the output value. Okay, so for example, you have 0 and 1 bit, and you're applying a AND gate, and you get 0 and 1 as an answer. 0 into 0 becomes 0, 0 into 1 becomes 0, 1 into 0 becomes 0, and 1 into 1 becomes 1. So gates are nothing but, gates are actually the transformation. So that transforms the input state to get an output state. So AND gate is there, and you have two bits, zeros and ones, and when you apply AND gate to the input state, it transforms the input state to an output state to get zeros and 1 bit, right? So that's what a gate is. And we have multiple gates, like in classical and quantum. We will see that in the upcoming slides. We need to understand the main functions, why classical gates are irreversible and why quantum gates are reversible. So there are different functions. You might have definitely studied this in your first semester or in your 12th standard. Let's quickly see what function actually makes classical gate irreversible, and what function actually makes a quantum gate reversible. Okay, there are different functions like one-to-one, on-to, bijective, and many-to-one. Okay, so one-to-one is, one-to-one means you have an input, and every input maps to a unique output. That's called one-to-one, an injective function. So different inputs actually have different outputs. You can see this in this diagram. In logic gates, in classical gates, NOT gate is actually injective in nature. So only to make it more precise, in classical computing, only NOT gate is reversible. So why NOT gate is actually directly used in the quantum as Pauli X gate, because NOT is already reversible in nature. Sorry, does anyone have anything to say?
Ma'am, I have one question, ma'am.
Yes, sir. Yes, ma'am.
Ma'am, I'm not getting bijective function.
Yeah, I'm coming to the point, ma'am.
Okay,
I'm
ma'am.
actually coming. I'm actually in one-to-one function only, and I'll come to the bijective function.
Okay, ma'am.
Okay, so a NOT gate is reversible in nature. So so we have already seen in the previous slides that most of the classical gates are irreversible, and only one classical gate is reversible. So what is the classical gate which is reversible? NOT gate. So NOT gate is reversible. So why we are directly adopting that NOT gate into the quantum as a quantum gate. So in quantum version, we are using the NOT gate as Pauli X gate. It's directly adopted. We don't have to do any. We don't have to convert into Boolean function. We don't need to put any extra Y bit, or we don't need to do any extra function. It's directly adopted because it's reversible. That's the power of reversibility. Okay. And many-to-one functions. So most of the classical gates, which are irreversible in nature, have this many-to-one functions, which means you have multiple inputs are actually pointed to one single output only. So your A input and B input only points to A output, which means, for example, you take an AND gate. What is AND gate? You remember the truth table, right? Let me dictate. So if you have two inputs in the AND gate, X and Y, we can keep X and Y. So 0 into 0 becomes 0. 0 into 1 becomes 0. 1 into 0 becomes 0. 1 into 1 becomes 1. So here 0, 0, 0, 1, 1, 0, all these inputs actually point to 1, 0, that one particular bit 0, right? So three inputs point to one output 0, and only 1 into 1 input actually points to 1. So those kind of gates are actually irreversible in nature, and we all understood why. We all understood that 0 into 0 becomes 0, and we all understood the truth table, but we may not understood what actually made it to be irreversible. Why the AND gate is in such a way? This is the main reason, because this AND gate follows many-to-one mapping. So every circuit, you have to remember that every circuit is designed according to the functions. Okay, so most of the classical gates follow the many-to-one mapping. This mapping follows. Okay, only the NOT gate is for only for NOT gate one-to-one mapping is followed. But this is completely opposite to the quantum side. So what do we do in the quantum side? In quantum computing, all the gates should be designed in such a way that every single input should have a unique separate output. And what do we call that mapping as? Bijective mapping. Okay, so if you are interested in circuit designing, you should definitely understand this kind of mapping, functions, and abstract algebra, because that's going to help you. Okay, so every input, you can see in this diagram that every single input is mapped exactly to every single output. So in this case, there is no information loss. If there is no information loss, then no output is left unused. So these functions are actually invertible, means it is actually reversible in nature. Okay, so why bijective function is used as a mapping in the quantum gates. Okay, so in gates, so the quantum gates which are used are NOT gate, swap gate, CNOT gate, Toffoli gate are actually used, are the main gates which are formed via bijective mapping. So I hope this is clear. So why we use bijective mapping in quantum computing, and why classical computing follows one-to-one and many-to-one mapping. This is the reason why classical gates are irreversible, and why quantum gates are reversible. Yes.
Ma'am, in this particular slide
Yeah.
regarding injective as well as bijective, the first statement remains one and the same, no?
Sorry.
In this particular slide regarding injective and bijective, the first statement, if you read,
Yeah.
every input has a unique output. For both, it is the same.
Actually, I can say you. Okay, so I can say here now in the injective one, right? In the output you have extra B output, right? So that is actually not mapped. So
Okay,
sorry,
okay.
this is an extra arrow I forgot to remove. I'm very sorry for that. It might be confusing you. So in the output you have an extra bit, right? B, that's actually unmapped bit. Okay, that's what 1 to 1 is. But in bijective, every input should be mapped with every single output, and there should be no extra bit in the output.
That
That's,
means unique mapping should occur from input to
yes,
output, whereas from output also reversibility to input.
exactly.
Okay.
I will actually show you how to do that, because I will solve that actually and show you in the when I share my iPad. I mean the
Okay.
screen, and I will show you how do you adapt that.
Thank
I
you,
hope
ma'am.
this is clear. Yes, sir. Thank you, sir. So now you understand, right? What is the importance of function? How gates are actually designed. So this is very important. When you are actually studying quantum, you need to always remember that functions going into deep technical mathematics can actually give you more insightful ideas. So that's the reason why I wanted to do these functions. It's very interesting topic to do, So, okay, coming back to the point. So why do we need to do functions? What is the importance of functions? So gates design follow the principles of function, and classical gates follow 1 to 1 and many to 1 functions, and quantum gates follow bijective functions. So when you use bijective function, these are reversible in nature. So why we use bijective mapping in the quantum side. Okay, fine. Let's come to the classical gates. We know all the classical gates like AND gate, NOR gate, XOR gate. So we don't have to spend too much time on this. Okay. So coming back to the reversibility. So again, as I mentioned many times, I might have said in past half an hour, classical gates are mostly irreversible in nature. Irreversible means loss of information, which means multiple inputs map to same output, like we saw in this many to one mapping, right? Because of this multiple many to one mapping, this you have irreversible. You can't reverse that. Output state to the input state, which means there is a loss of information. So in classical laws, loss of information isn't a problem. But in quantum mechanics, gates are designed to be unitary and reversible, as I already mentioned. So this means information is preserved and is not lost. So in quantum mechanics, the information has to be preserved and should not be lost. You should by this time you should think why irreversibility doesn't matter in classical physics but a serious concern in quantum physics. You might have already got this question. So to answer your question, in classical computer, information is actually stored in voltages, right? High and low voltages and transistors we use. Okay, if an AND gate outputs 0, it doesn't matter which input caused it, which means 0 into 0 also gives 0, 0 into 1 also gives 0, 1 into 0 also gives 0. So it doesn't matter from where that 0 output comes from. So the input doesn't matter, but it only needs the classical computer only needs the output 0 to do the next step. Okay, input doesn't matter. The input so the output 0 can be from 0 0 input also, 0 1 input also, or 1 0 input also. So that doesn't matter in classical computer. So the lost information doesn't break any computation. It just means extra heat is generated. According to the Landauer's principle, each erased bit dissipates kT ln to energy, which means K is a Boltzmann constant and T is an absolute temperature, and ln means we see that log, and 2 is like a twice the energy. Okay, so for every erased bit, K into T to the K into T into ln to energy, that amount of energy is dissipated for every one bit of information is erased. Okay. Since classical hardware is designed to tolerate power loss and dissipation, irreversibility is actually not a fundamental barrier in classical computing at all. Okay, so that's why irreversibility is not a problem in classical computing, but in quantum computing, this is a big issue, because quantum computer is still in the niche stage and it is not designed to tolerate the power loss and dissipation. Okay, because quantum computers are designed in such a way that it should every quantum chip actually is placed in a very cryogenic temperature. There should not be any heat. If there is any heat, then there is a decoherence and noise introduced. If there is a decoherence and noise in quantum hardware, then you don't get a stable measurement. If you don't get a stable measurement, there is no use of doing the measurements at all. So that's the reason why irreversibility is not a problem in classical computing, but it's a problem in quantum computing. Okay. Yeah. To explain again, in quantum physics, like the time evolution, a closed quantum system is governed by this Schrodinger equation. So this I of t equal to u of t. This is this nothing but I mean, this is actually not a Schrodinger equation, but if it, since it's a in Schrodinger equation you have an Hamiltonian. So when the Hamiltonian as time evolution, you have this you get this formula. Okay, so you need to actually follow this principle. So in this, what does it mean? So u of t is a unitary matrix. Again, coming to the point, unitary means reversible. Okay, so this is the formula for unitary. So u dagger. So this symbol is called as dagger. Dagger means you're taking the opposite of the of the matrix. So u dagger equal to u dagger equal to I. So that should be identity in nature, which means this should be irreversible. This is what reversible in nature. So that's why we say quantum should be reversible. Yeah, unitaries are always invertible. If gates were irreversible, we would violate basic physics. This is not a choice, but it's a law of nature. Yeah, yes.
U into U transpose, ma'am, that is
Yeah, it's a dagger, sir. Dagger.
transpose.
No, it's not a transpose. Actually, it's a dagger.
Okay.
Dagger. We use that in the quantum computing, sir.
Okay.
Yeah. So this is actually why you can ask me why quantum is like this, because this is not created by humans. This is a nature. This is not a choice. This is a law of nature. So quantum evolution must be reversible, and that's a nature that everyone should follow. That's how the nature is, and we all should abide by the nature rules, right? So that's the reason why quantum is like this and classical is like that. So if a quantum goes through information, sorry.
Dagger is transport conjugate or conjugate transpose?
Yes, conjugate transpose. Yes.
Yeah. A into a power theta are equal to a power theta and a equal to I.
Yeah, exactly.
Either theta or dagger.
Yeah. Hope this is clear. Hello.
Yes, ma'am.
Okay. Thank you. Yeah. So I think this slide is clear. Okay, now we need to know what gates are reversible and their equivalent quantum gates. So you have in classical gates, the reversible gates are identity gate and NOT gate. As I mentioned, NOT gate is injective in nature, where you give an input, you can reverse back that part, and identity gate is also actually a reversible one. So NOT gate and identity gates are reversible classical gates. So this is the reason why identity and NOT gates are actually embedded naturally into the quantum gates. Okay, so the NOT gate is adopted into the quantum version as a Pauli X gate, which also means a bit flip gate. X gate means Pauli X means bit flip gate, which we use in quantum. I think you might have seen this in the previous sessions, if I'm not wrong. Next, which classical gates are irreversible? A lot of classical gates are actually irreversible. Okay, so we will. So for this, I will explain you how does the classical irreversible gate is adopted into the quantum. Okay, let me quickly unshare my screen, and I will use the add rod, and then I will reshare my screen back. Is my screen shared?
Yes, ma'am.
Yes.
Shared.
You are seeing the black screen, right?
No, no,
Yes,
no.
ma'am.
It's,
Okay, thank you.
app is open.
So we can see how this is adopted. Just a second. Okay. So we take call classical AND. Okay. So this is the example I've mentioned in the presentation. So for the my screen is visible. You can see that I'm writing, right? Just a confirmation.
Yes, ma'am.
Okay. Okay. Thank you. So we can write the classical AND in the mathematical terms as x1 comma x2. Okay. So x1, this down symbol is actually the AND gate symbol. Okay. So this is the mathematical way of representing the classical AND gate. So for the two, so we can go with the truth table. Truth table of AND gate. So x1 and x2 are actually the input and AND is the output. As we have discussed already, that truth table 0, 0, 0, 1, 1, 0, 1, 1. So 0 into 0 becomes 0. 0 into 1 is 0. 1 into 0 is 0. 1 into 1 is 1. Okay. So you can see from this that 0, 0 also maps to 0. 0, 1 also maps to same 0. Okay. And 1, 0 also maps to same 0. And 1, 1 maps to 1. Okay. So this is clearly irreversible. Okay, so our major point is to make the irreversible to reversible form. How do we do that? We are introducing an extra bit. Okay, I'm just writing the mathematical equation for this. So f of x1 comma x2 comma y. So okay, I will explain it soon. 1 minute. x1 comma x2 comma y XOR into x1 comma x2. Okay, so your x1 x2 are the original input of the AND gate, and y is an extra bit we are adding it. Okay, and this is an XOR function. Okay, so this we can write it as x1 and x2 are actually control bits. It's preserved, and actually y is equal to, y dash is equal to y XOR gate x1 and x2. So this is very simple. Okay, in the previous page I've written y. Okay, y XOR x1 x2. Okay, so that's what I'm just introducing a variable x dash. Sorry, y dash. Okay, I'm just introducing a variable and storing that y XOR x1 x2 under this y dash variable. Okay, that's it. I'm not doing anything much. So that is a question here. Why do we actually use an XOR gate? Why do we actually use an XOR gate? This is a very important question one must ask. Okay, for that we can, let's go back to the properties of XOR gates. So just a quick revision. The truth table of XOR gate is A, B, A, XOR B. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. Okay. So in this, you can understand that 0 and 0 will be 0. Okay. 0 and 1 XOR 0 XOR 1 will become 1. 1 and 1 plus 0 XOR will become 1, and 1 plus 1 XOR becomes 0. So same bits means 0 and different bits means 1, right? So the rule number 1 is A XOR 0 will be A and A XOR 1 will be not A, not of A. Okay, so just it's very simple. So for example, you take A is 1, A1 XOR 1 is 0, right? Not of 0 becomes 1. It's a very simple formula. It's not even a formula, first of all. It's just a simple truth table. I'm just giving a very brief overview of why we are using an XOR gate for this. What is the use of using XOR gate? We have multiple other gates, right? Actually, XOR gate is also an irreversible gate. But when XOR gate is used with, when the XOR gate is used along with the extra bit Y, you actually convert that gate into a reversible form. This is also one form of intuition you get when you are understanding the mathematical form, mathematical side of quantum. Okay, now the rule 2 is, but I want to know how this is reversible. Okay, so next is rule 2. So XOR is irreversible. So we are writing x1, x2, and y, which gives you x1, x2, y, XOR gate, x1 and x2. Okay. So your x1 and x2 are preserved. So when you convert this formula, this is the same thing. Okay. So your x1, x2 inputs are actually preserved. It's not lost. So if it is not lost, means it is preserved. Preserved means the information is not thrown away, just like how in classical information the bits are thrown. Only when in classical computing, when the bits are actually erased, the entropy is increased. When the entropy is increased, heat dissipation happens, and that's what we have seen in Landover's principle. Okay. Now let's consider if y equal to 0. Okay, then again we can draw a truth table for this one. 0, 0, 0, 1, 1, 0, 1, 1. Okay. And here, this is the output. Y dash equal to Y XOR x1 and x2. So if y is 0, what do you get? So when y is 0, so y dash equal to y is 0, 0 XOR 0 into 0, you get 0. Y dash 0 XOR 0 into 1, you get 0. Y dash 0, 1 into 0, you get 0. Y dash 0 XOR 1 into 1, you get 1. Okay, so this is the how you get when y equal to 0. But I wanted to know whether this is reversible or not. I want to know if it's reversible or not. Okay. So, for example, you take when you do, we can take this part itself, this part, and we can check if it's reversible or not. So, for example, you take y equal to 0, x1 equal to 0, x2 equal to 1. Forward means we are just checking in the we are solving this once again, and we are seeing y dash equal to y XOR x1 and x2 equal to 0 XOR 0 and 1 becomes 0 XOR 0 into 1 becomes 0, right? So 0 XOR 0 is actually 0 in the XOR truth table, right? We all know that. So how do we know whether this is actually reversible or not? If it is reversible, then we need to get the original y back. We need to get the original y back. Only then we know that this is reversible. This method is working. Okay, how do we know that? So we can know that by reversing this formula. Y equal to y dash xor x1 and x2. So you get, so your y dash is a 0, xor 0 and 1, you get again 0. So you can understand. So you got y equal to 0. So when you do the backward, when you do the backward calculation, also you got y equal to 0, and the original value is also y equal to 0. So in that way we can understand that this is reversible. So this method actually works. This is how we convert, this is how we create a unitary version of the Boolean function, the one which I mentioned in the first slide, right? How do you convert classical irreversible Boolean function into the quantum adapted version of the Boolean function? This is the method. We are actually introducing extra qubit y, and we are doing XOR function. So we are getting, so that in that way the Boolean function becomes reversible. And also I proved with this steps. Okay.
And still that x1 and x2 is reversed, madam, actually.
Sorry?
X1 and x2 is the actually inputs. Y
Yes,
is an
sir.
added bit one. But you said the inputs are reversed. Is it can you explain that point, madam? X1 and x2,
Sorry,
you got
I can't.
y value.
Your voice is less audible, sir.
Madam, y value is you got the y value reverse back. How can you get the x1 x2 value back, madam? From
No,
the
actually
y value?
x1 and x2 are actually the input. Input should not be can't be done. I mean, this is not how we should be do. X1 and x2 are the inputs. The inputs are actually preserved, and we are adding the extra y gate. I mean the y bit, and then we are. This is the way actually to reverse the one. We can't do for the input bits and all.
Okay. Your argument was we are losing the inputs when we are in the classical one. In this quantum one, we are getting you are preserving the inputs, no, madam. How it is preserved?
In order to see, that's the point, sir, here I'm trying to make. You, if you want to make a irreversible into reversible one, you can't just directly make an input into, like, we can't do some other operations, right? You need to have an extra bit, and then you need to use the XOR function. So input can't be actually just like that, can't be changed into the quantum version. You, for that only we are introducing an extra bit, so the input is actually saved. There is not other way to even do such things.
Okay. Thank you, madam.
Is that clear? I know that it can be confusing. It can be confusing at first, but if you sit and intuitively understand, right, it makes sense, because it was confusing for me when I was studying at the beginning. But when you work in that field, right, you kind of understand like why it is prepared and had in such a way.
Okay. Okay. Thank you.
Madam, the second and third row, how do we figure out interchangeability of x and y, x1 and x2 here?
Sorry?
Well, second row, third row, output is 0, right? So how do we figure out x1, x2 value 0 or 1? How do we trace it back in second and third row?
Sorry, sir, your actually voice is a bit inaudible.
Okay, row number second and third, output is 0. How do we trace back values of x1 and x2, which is supposed to be preserved?
You have to do that like how I proved this by doing this operation, right, by taking y equal to 0. You have to do the same method to understand it, whether it is reversible or not.
Okay.
You have to repeat the same operation for different. For example, you have to take x1 equal to 0 and x2 equal to 1, and then you have to do it reversibly, and then you can get it back.
Okay.
So this maybe you can take this as one part of an assignment. You can understand that. You know, for this part, I proved. I mean, I used y equal to 0, and x1 equal to 0 and x2 equal to 1. If you needed to understand, you can go back and you can do this, take this, and you can do the same step which I followed here, and you can get the output results, and you can check it, how things work. I hope this is clear. This can be a bit confusing because this has not been widely taught in overall classes. Like I have done actually many research to understand how they're changing, how they're actually adopting their classical version into the quantum version.
Okay, ma'am. Please continue.
Okay, sir. Okay, so this XOR, so the AND gate, the classical AND gate, when you do these operations by changing, putting an extra bit and doing this XOR operation, it gets adopted and become a quantum gate called Toffoli gate. Okay. So how do you get the Toffoli gate? We will see that. So now we have seen if y, whether by using y equal to 0. Now we can see with y equal to 1, what will happen. So x1, x2, y, and then y dash equal to y XOR x1 and x2. Okay. So 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1. So it's y equal to 1. So if then we can do the same operation. 1 XOR 0 and 0 equal to 1. Y dash equal to 1 XOR 0 and equal to 1. 1 XOR 1 and equal to 1. 1 XOR 1. 1 XOR 1 into 1 and 1, it becomes 0. Okay. So when you come, so this is the result where you get when you use y when you keep an extra bit value y equal to 1, you get this answer. Okay, so if you combine this y equal to 0 and y equal to 1, you kind of get the Toffoli result. Okay, that quantum version of the gate is Toffoli gate. So let's combine x1 x2 y and then y dash equal to y XOR x1 and x2. So 0. So let's put all the values one by one. 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. So to be very clear, I'm putting that y equal to 0 value first, and then I will be putting y equal to 1 value first. Okay. So to avoid confusion, so these values are y equal to 0, and remaining values will be y equal to 1. Okay. And these are the results which we got when we are solving y equal to 1 and y equal to 0. Okay, these are the results which we got. We will be putting it here. This result is 0, this is 0, this is 0, and this is 1. Okay, this is 1, this is 1, this is 1, this is 0. Okay, so your from here you can understand, you get all the y. I will make, this is a very important step. So you can, from this table, you can understand that you get all the y as an output when x1 and x2, when the x1 and x2 control this in Toffoli gate, we call x1 and x2 are the inputs, as an input. Okay, so when an input, x1 and x2 are zeros and ones. Okay, I will explain it more clearly. If you see in this part, 1, you get 1 when the control is 1 And when the control and target is actually 1, the bit is flipped. You can see it here. So when both x1 and x2 inputs are 1, the y is flipped. Y is flipped to 1. So that's the main condition in the Toffoli gate. And that's how the Toffoli gate is formed in quantum side, by adopting the classical AND. If you take the Toffoli gate truth table, you can understand this. Okay, and the same happens for this also. When 1 1 means the output, the y is 1 here, and the output is flipped. Output is flipped when x1 and x2 are 1. But all the other are 1 only. Y as output. And this is actually the Toffoli gate. So the main condition is when x1 and x2 are their input, or in quantum term we say it as a control bits, and y is a target bit. So why I said y as an extra target bit. If you observe it clearly, I mentioned extra, y is an extra target bit. Okay, and x1 and x2 are the control bits. When control bits are 1, the target bit is flipped to 1. I mean, target bit is flipped. Here, both the controls are 1, so the target bit is flipped. The target bit here is 0 and it is flipped to 1. Same happens here. When both control are 1, the target bit is flipped to 0. And this is the main condition of the Toffoli gate. So this is how we get Toffoli gate from the AND gate. I hope this is clear. This can be a bit confusing because it involved a lot of other steps, right? So I will share these notebooks. You can definitely sit, and I will recommend to sit and understand intuitively. You will definitely understand that.
Yes, ma'am.
Okay. So yeah, and next is XOR gate. Next is an XOR gate. In the PPT, I've already explained these things, but I'm just explaining you by solving it so that you understand how a classical gate is adopted in a quantum version. Like, how do you actually change it? So the first step is converting an AND gate into a Toffoli gate. So that was the very large step we have followed, right? And we observed how come this has been changed. We can do it for XOR gate. XOR gate is very simple. We can just finish it quickly. So the mathematical term for XOR gate is x1 comma x2 gives x1 XOR x2. So the XOR we already know, and we have already seen the XOR gate truth table: 0 0 0 1 1 0 1 1. So 0 0 becomes 0, 0 1 becomes 1, and 1 0 becomes 1, 1 1 becomes 0. Okay. Now this is the classical version. Now we need to adopt the XOR gate into the quantum version. Okay. So when you adopt XOR gate, classical XOR gate becomes C0 gate. Okay. So how do we do that? In order to adopt the XOR gate as a quantum version, a new bit called target bit Y is introduced. So we can introduce that x, y, comma, f of x, comma, y. And then same method is followed, y XOR x. Okay. So your x is an input here, and y is a target bit. Okay. Now, if y equal to 0, we can write x, y dash equal to y XOR x. 0 0 0 1 1 0 1 1. Okay, so y dash equal to 0 XOR 0 becomes 0, and y dash, this is 1, this is 1, this is 0. So from this, you can understand that y didn't flip because x equal to 0. Y flipped because x is 1. So from the above, from this truth table, we can understand that when the control bit x is 1, target bit y is flipped. This quantum adoption as C0 gate is successfully applied. If you can see the truth table of the C0 gate and you get it. This is how you get XOR, how you adopt an XOR version of the C0 gate, like how you convert an XOR gate into a C0 gate. I hope this is clear, but it can be confusing. I understand that, but that's what quantum is. It's all about the math and a bit more deep physics. Fine. So let me. So does anyone have any doubts? Let me go back and share the screen for this PPT. Okay, so we have seen the quantum, AND gate adaptation as quantum gate. These are the explanation I have given here. I have solved all the explanations which is given here. So yeah, you get a Toffoli gate, quantum Toffoli gate here. And then this is an XOR gate, which just now we solved it. And then we get a quantum version of an XOR gate also. So this is what we solved right now. When x equal to 0, target y stays the same. When x equal to 1, it flips. Now coming back to the main point, we have seen the classical gates, the quantum gates. Some quantum gates are inspired from the classical gates. For example, classical NOT is inspired, since classical NOT is a directly reversible gate, it is used as a Pauli X gate. Yes?
Can you put in slideshow?
Sorry.
Oh, it's all right.
Okay, I just kind of forgot. Very sorry for that. Okay, so till now we have realized how to adopt a reversible gate into a quantum version as a reversible one. So some quantum gates are actually adopted from classical gates, like NOT gate is adopted as a Pauli X gate, and swap gate, classical swap, is adopted as swap, because these are directly reversible ones, so it can be embedded naturally into the quantum version. Okay, and XOR gate, just now we solved, is XOR gate is actually a C0 gate. When you add an extra Y bit and do the XOR operation, you get a C0 gate. And then the AND gate is Toffoli gate. We also solved that. So some quantum gates are actually inspired from the classical gates, but there are actually some pure quantum gates which are not inspired from the classical one. Those are Pauli Y gate, Pauli Z gate, Hadamard gate, phase gate, and rotation gates. Those are purely quantum in nature, and they don't have any classical part in it. Okay. Yes. So we actually reached the end of the session, and yeah, I hope today's session was a bit more clear, and I've given some input and value of how we are using the Boolean functions, how Fractal is formed, how do we actually convert a classical irreversible gate into the quantum reversible one. We solved the classical AND gate, which is irreversible in nature, into quantum gate as a Toffoli. We got a Toffoli gate from an AND gate by introducing an extra Y bit, and then we are doing XOR operation. We combined two values, y equal to 0 and y equal to 1, and we got the Toffoli old Toffoli gate itself. Okay, so in Toffoli gate the main condition is two, when two controls are 0, when control bits are 1, the target bit flips. So that's what we saw in the Toffoli gate, and that's the main condition. We saw how XOR gate is converted into CNOT gate, which is a CNOT gate is a classical quantum gate. We saw how it is adopted. Okay, and we also saw how what gates are actually purely quantum: Pauli Y, Pauli Z, Hadamard gate, phase gates, rotation gates. Those are actually an S gate, SMT gates are actually S dagger, T dagger. All those are actually purely quantum gates. You know. Yeah. That's the I hope everything is clear, and I will share all the PPTs and the notebooks also, so that it's very helpful for everyone.
Ma'am, somebody has a question in the chat. What is ancilla qubits?
Ancilla qubit is the extra qubit we are adding. Ancilla qubit is actually an extra Y bit we are adding. Hello.
Any questions from the participants? Any questions? Ma'am, somebody asked classical swap means.
Swap means you're just swapping. I mean, for example, if you have a 0 this left side and 1 that side, for example, you're having 0 on the left hand and 1 on the right hand, you're just swapping the left hand and right hand. So one comes to the left hand and 0 comes to the right hand. That's what swap means.
Okay, ma'am. Any more questions? Any more questions?
Sir, I have a query.
Yeah, please carry on. Sir, please ask the question. It is open. You can ask.
Here we are adding the extra bit only to reverse it, ma'am.
Yes, sir.
Okay.
That's what we use it. That's the reason why we use Oracle to adapt into the quantum version. Because classical, that's the reason. Classical gates are irreversible in nature, which means you need to adapt into the quantum version. How do we adapt? By adding an extra bit called extra target bit called Y. So why we call target? Actually, there is something called target. Target bit is actually used in quantum. I mentioned target bit because target bit is the extra bit we are adding, and then along with the XOR operation. So that actually makes the whole operation to be reversible. And it is adopted according to the quantum side, according to the quantum gates.
That
so
extra bit,
yes, sir.
Extra bit may be anything, huh?
Sorry?
Why may be anyone, any number?
Any number means you have one. I can understand.
You have kept Y all zeros and in one case and Y all ones in one case. Whether it can be any number.
No, sir, because it's a Boolean function. Now that's the reason I was explaining. Because that's the reason why I explained Boolean function. Boolean function takes zeros and 1 only. We can't take 2.
Okay, madam. Can the Y value can be varying for case to case, or it should be all the same?
Y, for example, I have explained Y equal to 0, and for 0, 0, 0, 1, 1, 0, 1, 1, we use Y equal to 0, and again we can use the same Y equal to 1, and we get the Toffoli. Total operations, we get it. When we combine Y equal to 0 and Y equal to 1, we get all truth table of the quantum gates. For example, I have shown in the AND gate that by using Y equal to 0, we got some truth table, right? So in Y equal to 1, we got another truth table. So when we combine Y equal to 0 and Y equal to 1, we get a quantum version of the quantum gate. So in AND gate, when it is converted into quantum gate, it becomes a Toffoli. It becomes a 3-qubit gate. Does it answer my question, sir?
Yes, madam. It's okay, madam. Whether that the reversible is like error checking, that is whether we can retrieve certain cases only, or you can retrieve the entire input, madam, or like verification of the input, or it can be able to check every cases.
Yeah, we can check every cases, actually.
Okay.
I just took an example and showed you that you got the Y back.
Yes, thank you.
The inputs are actually preserved. We can't touch the inputs to check the reversibility. We should only check whether the Y we are adding is reversible or not. Only then we can understand whether this actually is adopted into the quantum motion.
Got it.
Sorry for asking another question also, madam. That is,
yes.
It is like adding an extra parity bit to your Hamming code, because I'm new to this quantum computing, madam. I'm just having an idea about the Hamming code. Is it similar to that kind of code, madam?
You can say, sir. I kind of forgot like the electronics part, but if I'm not wrong, that should be the case, because it is adopted from the classical one, right? So it should more or less be same.
In a networks part, you will say that parity bit is to check the or checksum bit will add up to check whether the error have happened or not. Is it like kind of thing, madam?
Maybe, sir. I am not very sure about it. I kind of it's been long time that I completed my bachelor's, and I'm lost touch with these networks and all. So I'm very sorry about that.
Sir, okay, madam. I'm taking it as an information that it is like in error correction or error correcting code. We are adding an extra bit, madam. Is it okay, madam?
No, sir. It's not error correcting code. It's just we are actually adding that to adopt it, because that's the way that researchers have found a way to adopt some gates into the quantum gates.
Okay, I have to read more.
If you take the quantum gates, right, there will be one single qubit gate and multi-qubit gate. So AND gate, when you include extra Y bit, it becomes a 3-qubit gate. Toffoli is actually a 3-qubit gate.
Okay, madam.
It can be confusing, of course. It should be confusing, because everyone is in the learning stage, right? Even I'm in the learning stage, and I sometimes get confused why this is like that, because learning is a non-linear process, and we can't understand everything at once. So I completely understand the doubts and all. Even I had the same doubts, and I did a lot of self-study to understand.
I have a question.
Yes.
Yeah, please carry on. Somebody is asking question.
Carry on you first. It's okay.
Okay. Ma'am, can you tell us anything about Pauli Y and Pauli Z gates?
Yes, so Pauli Y is actually you add an extra phase where when you convert when you have a certain condition. I think isn't it covered in the previous session, sir? I thought it was covered in the previous session, Pauli Y and Pauli Z gate and all. Isn't it covered, sir?
Actually, police excuse was mentioned, ma'am. Police excuse was mentioned, and police Y and Z he said like they are similar, but they're actually easy, ma'am. Could have understood that.
So you want an explanation for Pauli Y and Pauli Z gate, sir?
If possible, ma'am. If possible, ma'am.
So okay, I can give you that. Just a second. So Pauli Y and Pauli Z gate, those both gates are actually completely quantum in nature. So Pauli X gate, we all know that it is classical. From C0 gate, NOT gate, we adopted Pauli X gate, but Y gate is also very similar to the X gate, but it has a negative amplitude I. When the negative amplitude I is multiplied to the output, you get actually there is some kind of truth table involved to explain it. Do I need to do it, or should I need to do it by sharing the screen? I think
no issue, ma'am. No issue. Just theory is okay.
So, for example, you have gate 0 and gate 1. Okay. So in Pauli Y gate, when the input is gate 0, the output is actually I into gate 1. So Y gate is actually like a NOT gate. When you give 0, the bit is flipped, but along with the bit flip, the imaginary amplitude I is also multiplied. So you get gate 0, when in the output you get I into gate 1. I is nothing but an imaginary amplitude multiplied to the gate, that particular state. So you get I into gate 1. And when the input is gate 1, when the input is 1, the output is actually minus I into gate 1. So the negative amplitude is multiplied when the input is actually gate 1. So to be very simple, Pauli gate is nothing. Pauli gate is a combination of Pauli X gate plus a negative amplitude. Negative amplitude multiplied when the input is gate 1. So that's what Pauli Y gate is. And Pauli X gate, Pauli Y gate, everything is unitary. You can, if you take Y dagger, Y, because you have a matrix for Y, Pauli Y gate, and if you take a dagger for Y gate, you get the same, identity operator, which means if you get an identity operator, it means it is reversible in nature. The gates are reversible. Atom gates are reversible. When you take the dagger of the particular gate, you get an identity operator. Identity means you get the same result. The same input what you get. So now coming back to the Pauli Z gate is nothing but a state transformation gate. So Pauli Z is not related to Pauli X and Pauli Y gate, but it's a Pauli X and Pauli Y are bit flip gate, but Pauli Z is a phase flip gate. When the input is gate 0, the output will be same gate 0. But when the input is gate 1, the output is actually minus gate 1. So the minus values minus value is multiplied to the state, to the output state when the input is gate 1. So 0, 0. So input is 0, output is also 0. When the output is 1, when the input is 1, the output is also becomes minus 1. So Pauli Z is more about the phase flip gate. And when you again take the dagger for the Z gate, you get the same identity gate.
Ma'am, can we change the number of inputs when we convert the classical gate into the quantum gate?
Number of input means?
That means we have, in the example, we have considered as, suppose we have considered an XOR gate, and there are two inputs, X1 and X2, and output is Y. And when we convert it into Toffoli gate, CNOT gate, so we have considered only one input and the other one is target. So can we change that one to two inputs to one input?
Yeah, actually for the XOR gate, you can implement a single output XOR gate. You can actually do that for the XOR gate.
Okay.
You can do that, because if you if it's a single input XOR gate, you get a CNOT gate. If you have two input XOR gate, you get a double CNOT gate. That's possible.
Okay, as we see that there is an ambiguity in the outputs, like there are number of zeros and number of ones from where we cannot exact find which input we take. So is it it will consider under the test cases that we consider all the cases to check the reversibility?
You can take all the inputs and you can check the reversibility. How I explained, right? If you take Y equal to 1 and you take different inputs, X1 equal to 1 or X2 equal to 0, if you take different kind of input also, you can check the reversibility. If you follow the same steps as I mentioned, you can get back
that means we cannot say that if the output of the quantum CNOT or Toffoli gate is 0, the properly input values are this. We cannot say that, right? Right? Because there are number of outputs that value 0. So my question is that we cannot say the particular input values with respect to the output value 0. We have considered all the cases where the output value is 0.
Yeah, actually.
So, ma'am, how can we say that it is reversible in form, because there is no unique output for the one particular unique input? as the bijection is not there.
No. This is actually a bit different. I actually will cover this in the next session, because this is one kind of doubt which I also had. Okay, so tomorrow I have this session. I will definitely cover this doubt in the next session, because tomorrow I have Simon's session to cover.
Okay, ma'am. Thank you so much, ma'am. Consider the this query. Thank you so much, ma'am.
Yeah, thank you. Okay, so anything else?
Any more queries?
Madam, I have a query.
Okay.
Yeah, regarding whatever the bits and gates that you have given with the classical computer related ones, and you have mentioned about the energy efficiency related to the physics and whatever the excited bits that you will be using in the quantum computing. So how that the energy will be a part in evaluating the gates instead of the classical computing, we'll be using a silicon gates or something else, so that the energy can be regulated. If the bits, whichever we are using in the quantum computing, is electrically or something like a excited bits that you are connecting, how the energy will be calculated there?
There is actually, sir, there are different ways of implementing the qubits in quantum hardware. It's like in classical we use semiconductors, right? It's in quantum there is a different ways of implementing. For every method there is a different way of calculation. For example, you can implement qubits in semiconductor spin qubits. There is superconducting qubits. There are neutral atom qubits, travel ions, photonics, and and NV center in diamonds. There are a lot of different ways to implement qubits. So the energy calculation can be different for every qubit actually.
That means using an algorithm with using a different gates can result in a different output, or whatever the outcome that you are using with the efficiency can be changed with the type of gate that you are using.
Yeah.
My question is similar to the concept of the space complexity and time complexity we are calculating. Should we have to do the same thing using the quantum computing also, with less number of steps and less number of gates?
Yeah, actually, yeah, there is a different complexity, time complexity for the quantum computers. So, for example, in Simon's gate, you need to the time complexity becomes polynomial in nature, which is a bit more good. I mean, better than the classical versions.
Okay.
Hello, ma'am. Am I audible?
Yes, you're audible.
Ma'am, there is one gate control, C0 gate in quantum.
Okay.
So it is based on 2 qubit. One is control and one is target. So when we use that gate in quantum image representation to draw the quantum circuit, it is very sensitive to noise, and it will sometimes give us a scalability issues. So how to overcome it, or can you suggest any alternative gate to represent a quantum image?
I have to see the problem first. Then I can only say the solution for that. Do you have any papers, or do you have any research? Advancements you have done, progress you have done in that?
Yes, ma'am. I have used 2 techniques: flexible representation of quantum images, and second is one novel enhancement of quantum images. In that, I have used some C0 gates and Hadamard gates. So when I use multiple C0 gates now, it is very sensitive to noise. Means we cannot store any blur image or the image where there is no discrimination of background and foreground.
Then the circuit depth is you have to reduce the circuit depth by implementing gates which are, for example, if you implement there is actually set of gates. If you implement, you get an output in a much more efficient way. You need to check with that. You need to reduce the circuit depth. If you reduce the circuit depth, you can actually get much better results.
All right, ma'am. Thanks.
Yeah. That's one suggestion I can give you. Since I don't know what actually you're doing, so this suggestion you can take it and you can think about it.
Okay, ma'am.
Okay. So
thank you, ma'am.
Thank you
very
sir.
much for your interactive sessions.
Thank you,
we
sir.
learned a lot from you.
Thank you, sir.
Thank you very much, ma'am.
Thank you, sir. Thank you. Let's meet in the next session. Thank you. Thank you all. Bye.
Bye, ma'am.
Bye.
Once again, good evening, participants. Now we are going to have the 6th session taken by Aniruddha Biswas sir. Sir he is already working in the building real world business oriented quantum computing solutions for banking, finance, insurance using IBM Qiskit, annealing, analog neural atom, Pascal based quantum computing, etc. Now I request Anirudh sir, please start sharing his screen and start the session.
Yeah, thanks, Professor Murthy. So, am I audible?
Yes, sir. You are audible.
Okay, great. So, hi everyone. Good evening. So, thanks for having me here. So, today, I think the previous speakers already have covered a lot of other things. I've been starting from brief of what exactly quantum computing is, and probably they already have jumped into a lot of other stuff as well. So, let me know, please, if my screen is visible to you or not.
Yeah, it is visible.
Yeah, so.
Sir, it is clear.
Sorry, what?
It's clear. It's clear.
Yeah, sure.
Clear.
Okay. So, I think all my speakers have already covered a lot of things, starting from what are the basics of quantum computing and what are the quantum gates are and what other things are. I mean, what exactly the basic idea of how to write a quantum code and everything. So I'll not be getting into all those basic stuff that what exactly qubit is, but if you have, you can anyways ask some questions on that. So, I mean, what exactly qubit is, what is block sphere, so what exactly gates are. So I believe most of the people already are pretty much aware of it because already there's 6 sessions. So I believe that previous speakers have already covered it. Okay, so I'll straight jump into what exactly the agenda of today. So I think you can sense the basic agenda from the title itself. So exactly what exploring the quantum speed up from Deutsch to George-Josephson algorithm. So before getting into that extensively, so we'll jump into some maths, I don't have much slides, okay, first. So I